Good. I will start with the introduction. Thanks everyone for joining this seminar from the Cambridge Ellis unit. I would like to start by thanking the sponsors of the unit. We are really thankful for their support. I also want to introduce today's speaker is Po-Ling Loh. She's a professor here at Cambridge in the Department of Pure Mathematics and Statistics. And Po-Ling graduated in math from Caltech and then did a master in computer science and a PhD in statistics at UC Berkeley. She was from 2014 to 2016 assistant professor in the Department of Statistics at University of Pennsylvania. And from 2016 to 2020, she was an assistant and then associate professor at University of Wisconsin-Madison. She was also visiting associate professor at Columbia University. And in 2021, she joined her appointment here at Cambridge. And today she's going to be talking about differential private M-estimation. So I'm going to stop sharing my slides. I think, Po-Ling, if you want to share your slides, we can start.
Why is this paused? Hang on. I think I have something with the slideshows in the other desktop. Let me fix that.
I think we are not recording. Tim,
there we go.
can you confirm?
I think it is recording, right?
Let me see, click on record.
Sorry, it says it's recording on mine, so.
Okay, no problem.
Okay. Well, thanks a lot, Miguel. So I'm very glad to be here. I'm hoping to be more engaged in the Ellis unit at Cambridge as time goes on. I think there's not that much interaction between math and computer science. So I'll be talking about some work that I guess it sort of spans math and computer science. Well, statistics and computer science. So this is joint work with Marco Avila Medina. He's an assistant professor of statistics at Columbia University. Casey Bradshaw is finishing up. She's a PhD student in statistics at Columbia, and Jung Liu is a former student of mine at UW-Madison. So this talk is on privacy, and maybe let me take a little bit of time to review some of the basic concepts in privacy. As you may be aware, there is this definition called differential privacy that is a property that is desired of certain estimators. Well, I guess algorithms in computer science speak estimators as a statistician. So you compute an algorithm A on the data set X, and the property is that if you perturb the data set by a little bit, by 1 point to X prime, then the output of your algorithm shouldn't change too much. And as we'll get to in a moment, the way that you ensure differential privacy is usually by adding some sort of random noise. So we think about these algorithms as being random. And the property specifically is that the probability that the algorithm applied to X has a particular output should only change by a multiplicative factor of e to the epsilon and an additive shift of delta. So generally, small epsilon and small delta ensure very good privacy, because if epsilon and delta were both 0, then that means that the outputs are exactly the same. So that's very, very private. Now, one of the most basic concepts in differential privacy that you'll learn about right after the definition is something called the Laplacian mechanism, or the Gaussian mechanism. So let's talk about the Gaussian mechanism. The Gaussian mechanism is a way of making a particular function or a statistic private. So for instance, if your goal is to privatize the empirical mean, the idea is that the empirical mean itself is quite sensitive to individual points. If you change 1 point by a little, if you change just 1 point, you can make the empirical mean shoot off to infinity. Well, the first thing you assume is that you have some kind of a bound on the domain of the data. So if you have a bound on the domain of the data, that means that changing 1 point can't make everything shoot off that much. So if your statistic has a bounded sensitivity, then what you can do is you can privatize by adding Gaussian noise. And the amount of Gaussian noise you should add will be proportional to the sensitivity on your data. So for instance, the bound of your domain, and inversely proportional to your privacy parameter. So inversely proportional to both of your privacy parameters because there's an epsilon and a delta. And this is called the Gaussian mechanism because you're adding Gaussian noise. Another mechanism that's quite popular is the Laplacian mechanism. And just in a word, the reason why people use Laplacian noise instead of Gaussian is because the very first definition of differential privacy just had one parameter epsilon. There was no delta. And in that case, a way to privatize a function that has a bounded sensitivity is to add Laplacian noise with a parameter inversely proportional to epsilon. Okay, so in our analysis, we're actually going to use a slightly different framework of privacy. I'm not going to go into this in too much detail because Gaussian differential privacy is a pretty deep field, and it's a little bit subtle exactly what the concepts are. But very briefly, this is a framework that was introduced by a group from University of Pennsylvania. The second author is Aaron Roth in computer science. Third author is Wei-Jie Su, who's a statistician. And the idea is to look at a hypothesis testing viewpoint of differential privacy. And this hypothesis testing viewpoint is, well, if an algorithm is private, then it has a hard time distinguishing between whether the underlying data set is X or the underlying data set is X prime based on the output of your algorithm. So statisticians Larry Wasserman and Shuheng Zhou quite a while ago showed that if you have an epsilon delta differentially private test, then this test, which is going to be a function of the input data X, will have a bound on its power. So just to remind you of the statistical terminologies, right? High power means that it's easy to distinguish. So the point is that if something is differentially private, then it should be hard to distinguish. So for a particular type 1 error bounded by alpha, there's a maximum on the amount of type 2 on the level of power as a function of alpha and a function of your privacy parameters epsilon and delta. So Dong, Roth, and Su in this 2022 paper thought about it as, well, if we think about a hypothesis testing viewpoint of privacy, then we could think of any function of alpha and some privacy parameters. Maybe there are 2 parameters, maybe 1 parameter. And that's how they came up with this particular, so for a particular trade-off function, which is a function of alpha and the 1 parameter mu, you end up with something known as Gaussian differential privacy. Okay, but you could also have a whole family of possible notions of differential privacy according to what the function is for the bound on the power. And the reason why people like Gaussian differential privacy, but again, I'm not going to go into this in too much detail, is that, well, it turns out that when you want to ensure privacy, you put together lots of different building blocks which are known to be differentially private. In this talk, we'll be talking about doing gradient descent, where you keep adding some Gaussian noise. So you keep on injecting this amount of privacy. And the problem is, if every time when you do another operation, like a gradient descent step, if you look at your data again, then that leaks a little bit of privacy. So you need to find a way of controlling how much overall privacy loss do I have, right? Because you want to be as close to 0 as possible. And the nice thing about Gaussian differential privacy is that it composes very, very well. So on that note, the two things.
One question, just to clarify, you mentioned this Gaussian noise.
Yeah.
And could you say a few words about exactly where you add the Gaussian noise? It seems that you add the Gaussian noise to whenever you get some function that it depends on the data. Is that right?
Right. So yeah, so in the most vanilla version, right, I mean, it's sort of like you want to make the empirical mean private. So instead of outputting the empirical mean, you output the empirical mean plus some noise. And as we'll see in this talk, the idea is that, well, if you do a gradient descent on an empirical risk minimization problem, then every gradient you're computing is a function of your data, and it's an empirical mean of something. So then what you do is you add some noise every time you're doing that gradient descent step.
So
to mask the data.
Your gradient will be corrupted with noise every time.
Exactly.
Okay.
Yeah. You want to inject a little bit of noise to make it sort of, to occlude what's going on. Okay, so without really talking too much more about Gaussian differential privacy, there are just 2 things you need to know moving forward. The first one is that Gaussian differential privacy also has a notion of Gaussian mechanism. Okay, so if you have a function and it has bounded sensitivity, again, in the context of mean estimation, if your domain is bounded, Then if you add Gaussian noise, where now the noise you add is proportional to the sensitivity and inversely proportional to the one parameter of privacy, then you get Gaussian differential privacy with parameter mu. And then the second thing we need to know is how things compose. Okay, so if you keep on doing little steps, which are themselves differentially private, then if you compose this all together, the overall privacy parameter you have for your algorithm, it turns out that it composes actually tightly as square root of the sum of the squares. Okay, so that was sort of the intro to privacy in general. Of course, privacy is something that has been studied in theoretical computer science for quite a while. Statisticians have more recently entered the picture, and at least, so my viewpoint of this is that, well, in statistics, right, you're not just interested in making an algorithm private. So, you're not just interested in making a clustering algorithm private or a PCA algorithm private, or you're interested in estimating an underlying parameter. So the statistical framework is that you want to figure out a way to estimate an underlying parameter so that with high probability, your output of the private estimator is as small as possible. Okay, and it's not the first time that people have talked about private parameter estimation. There was a bit of work in computer science by Karwa and Vadan in 2018 that focused on private mean estimation. But I think what really made statisticians pay attention is a paper by another group from UPenn. So the first author is Tony Tai, and Lingjun Zhang is now at Rutgers. He does a lot of statistical work on privacy. And taking a statistical perspective, right, when we talk about optimal estimation, you often are interested in what are called minimax rates. Okay, so the minimax rate is saying, well, what are some high probability bounds on how good an estimator does? Where the max is taken over all possible parameters and all possible distributions in the class, and then the min is taken over every possible estimator you could have. Okay, so if you're trying to do something like mean estimation or linear regression, then the sort of minimax rate that you would get with no constraints of privacy or anything is something like square root p over n, where p is the number of dimensions and n is the number of samples. And now if you think about it as a minimax problem, where again, the max is over every possible parameter and class of distributions, but now the min is not over every estimator, but it's over every private estimator. Then what was derived in this paper was that the minimax rates, they grow because your min is over a smaller class. They have to be now private estimators. And the cost of privacy comes out in this additive way. Okay, so in the context of epsilon delta differential privacy, they had some results that characterized the new minimax rates for various statistical estimation problems. And actually in their work, so their work very much inspired ours. And as I've sort of hinted at, there was some notion of this private gradient descent. So we built upon this, and maybe the best way to summarize it is we were trying to relax some conditions and get rid of the necessity of tuning certain parameters. And the conditions we were trying to relax are sort of related to boundedness on the data set. Okay, but maybe this will become a bit clearer as I proceed. Okay, so this talk sort of overviews two different papers. The first one is in a low dimensional setting. And this is a paper that's already completed. Then there's the high dimensional setting that I'll segue to, which has been work in progress for quite a while. So the low dimensional setting, I think this illustrates the main ideas. And what we want to do is we want to use some ideas from robust statistics and bring them into the context of privacy. So there's there's a research agenda I've been pushing for the last couple of years, which is that there's some analog between robustness and privacy. So maybe let's talk on a philosophical level for a moment, right? So differentially private algorithm is something that doesn't change that much if I perturb one data point. And robustness, well, there are different definitions of robustness. In statistics, there's a long theory of robustness that dates back to the 1960s. And it also has some notion of stability to perturbations, usually perturbations in the population level of your data. And so the rough philosophy is that methods that work in robustness have some analog that works well in privacy and vice versa in many cases. And my collaborator, Marco Avila Medina, also has a background in robust statistics. So many of you have probably heard of M-estimators, even if you're not a statistician. But what might surprise you is that M-estimators actually come from robust statistics. And the idea with an M-estimator is simply that you're you're minimizing a sum of a function applied to IID draws from something. So we also call this empirical risk minimization. And the idea is that the loss function itself might vary. So in usual least squares, you would have a parabola. But the types of loss functions that were quite popular from robust statistics are losses like the Huber loss, which is quadratic and then becomes linear, so it doesn't grow quite as fast. Then there are also losses like non-convex ones like a Tukey loss. So the idea is that if you have data that are contaminated, then maybe you shouldn't be using something like least squares because the loss function grows too fast for bad outliers. And there's a very deep theory of all of this in robust statistics. So just to sort of recap this, right? In robust statistics, we usually study these M-estimators where the loss function has the property that the derivative is bounded. So that's what gives rise to something like a Huber estimator. If you think of the quadratic, the least squares loss function, well, the derivative of that is linear, so it's unbounded. Now, if for some reason that it can be made rigorous, we want a bounded loss, a bounded derivative loss. You can take your straight line, which is the derivative of the quadratic, and you can truncate it. And if you take the antiderivative, you end up with exactly the Huber loss, right? And as I said, there's elegant theory for why we want bounded derivative loss functions. So now the point is that if we're trying to do private estimation, having these bounded derivative loss functions is actually good as well. So here's the gradient descent algorithm sort of written out, where you take gradients, and now when you're performing these iterates, well, your empirical loss function applied to theta t, so that takes into account, I mean, that's computed on the real data set x1 up to xn, for which you don't want to have any privacy leakage, right? So whenever you calculate these gradients in your gradient descent routine, you're looking at the data again. And in order to make sure that this step itself is private, you need to do something to make it private. And what you would like to do is add something like a Gaussian mechanism. Okay, but the caveat is the Gaussian mechanism is great as long as you're taking an average of bounded things. And in general, you won't be, right? Because in general, if you have a loss function, like let's say it's a quadratic loss function, and you compute it on unbounded data, then the derivative is unbounded. And this is exactly where this robust statistics idea is useful, because if you now are trying to minimize using gradient descent, some kind of empirical risk minimization problem, and you replace your loss function, which has an unbounded derivative, by something like it, which has a bounded derivative, like a Huber loss, and then you run this algorithm, then everything is going to be private. Okay, so this idea of noisy gradient descent for privacy is a very old, well, I mean, it's a well-established idea. It has been studied a lot by computer scientists in theoretical properties, but most of the previous work has focused on bounding excess risk, whereas what we're looking at is specifically the problem of parameter estimation, right? And you can usually import excess risk bounds over to parameter estimation bounds, but then you might need to make assumptions on your loss function that you don't necessarily want to do. Okay, so that's the idea behind what we did. And then in terms of the actual mathematics, well, both Marco and I have lots of experience in statistics, sort of analyzing different iterates of optimization algorithms under certain statistical properties. So what we did was we looked at the actual rates of convergence for this noisy gradient descent, where we're using loss functions such as a Huber loss. And what you can show is that the number of iterations that you need is going to be logarithmic. And then with high probability, you end up with an output, which is, so here you see the cost of privacy, right? You see the part that's the minimax rate without a privacy constraint, and you see an additive part that depends inversely on the privacy parameter. Now, I said that we were using Gaussian differential privacy, but if you did the same sort of analysis with epsilon delta differential privacy, you would get something that's sort of in spirit, a similar result. You might wonder, so one thing that I want to point out is, well, in the cost of privacy paper that I mentioned on a previous paper, the one that got us excited about this, so they also analyzed some version of noisy gradient descent, but the idea was that in order to make sure that these iterates, that these gradients were bounded, what they did was a trick that is often used in privacy, which is that you just truncate things. Okay, so if you don't necessarily have a bounded gradient, you can say, well, I'll just choose some truncation parameter, let's call it gamma, and truncate. And then I know that everything is going to be sensitive up to this magnitude of gamma, so I can add noise that's inverse of gamma. But the problem is that every time you do a gradient iterate, you're going to have to choose a truncation parameter. And it gets a little bit messy. Whereas in our work, we sort of choose a Huber loss, which has a particular parameter, let's call it gamma, and we have a principled way of making this choice that depends on the problem parameters. Okay, and then since we were analyzing optimization algorithms, we also looked at second order algorithms. And of course, the story is something like if you have stronger assumptions on the niceness of your loss function, then you can get faster convergence. So something like log n iterations. I should also say that, so I think it's roughly, it's pretty recently, so maybe like in the last 15 years-ish, that statisticians have started looking at the optimization story. So classically in theoretical statistics, people talk about, let's say, the global optimum of your M-estimator and don't really care about how you would find that. You know, if it's convex, great, but even if it's not convex, like we don't really care. So it's become sort of in vogue, and also in some of my work, to try to analyze the exact path of some optimization algorithm that gets you to a global optimum of an estimator. But in privacy, it is extremely crucial that you actually analyze these iterates and you analyze how many you do. And the reason is that every time you do an iterate, you lose something. You lose a little bit of privacy. Your privacy parameter grows. So it's actually very important in analyzing these sorts of algorithms to be able to say up front, the number of iterations I need is blah, or order of blah, because then you can guarantee, then you just set your privacy budget accordingly. Okay. So, so maybe to kind of bring out a little bit more these ideas of how robustness will allow us to avoid certain problems. So I talked about using a loss function like a Huber loss, and it turns out that using a loss function like a Huber loss, it protects you against a certain type of unboundedness. So if you're talking about a regression problem, then in classical robust statistics, people talk about bad behavior in the X direction and in the Y direction. So the milder form of contamination is in the Y direction. That's like, you know, you're doing regression and you just have some small deviations or some small or large deviations away from the best fit line. But what can throw you off even more is to have deviations in the X direction. So these are called high leverage points, and that can like completely mess up your best fit line. So similarly, in our work, if you simply use the Huber loss, then that gets rid of the problem of needing boundedness in your response distribution. But if you also want to avoid boundedness in the X direction, which we realized we could sort of throw into our theory altogether, then there are other tricks you can use from robust statistics. So the idea is that when you calculate these loss functions, you don't just apply them to the residuals, but you apply them to some function of the x's that sort of downweights badly outlying points. Okay, and then I won't talk about this here, but some other nice theory that came out of this was that, well, I mean, in statistics, people care about confidence intervals as well. And from the theory of optimization of M-estimators, you can also pull out a private confidence interval. Okay, so now let's talk about the high dimensional setting. So for someone like me who's been working in high dimensional statistics since the PhD, this is a very natural question, which is, all right, so you have these results and they say that the rates are like square root p over n plus something. In high dimensions, when you do linear regression, you use L1 penalization sort of as a first cut. And the estimation error is something like square root k log p over n, where k is sparsity and p is dimensionality. So can you do a similar trick here, where you're trying to add a penalty in some strategic way, and then add noise to make things private? Okay, so what do people do in the high dimensional setting? Well, if you add an L1 penalty to something, you can't just do gradient descent, because the L1 penalty is not itself differentiable everywhere. So there are various tricks people use. Maybe one you might just pull out is something like subgradient descent. But another one that is often analyzed in high dimensional statistics is what's called composite gradient descent. So the iterates look like this formula I have here, but maybe it's worth sort of describing things in a geometric setting. So essentially what you do is you approximate your objective function by a quadratic, and then you minimize that quadratic instead. Now, if you did this in the regular non-penalized setting, you would get exactly gradient descent. But in the high dimensional setting, when you have an L1 penalty, you can't approximate L1 by a quadratic, so you just keep it there. And you approximate the smooth part of the loss by quadratic, and then you minimize the combined thing. And each one of these minimizations is going to be convex, obviously, but not just that, it has a nice closed form solution, because you're not just minimizing a quadratic plus L1, you're minimizing a particular quadratic that, I mean, it has Hessian equal to identity and so on. Okay, so what we do is the very natural variant. So you look at this iterate and you say, well, every time I see a gradient, I look at the data, so I need to make that private. So you add some noise. Okay, so it's very easy to state. It's not quite so straightforward to analyze as we discovered. So what noise do we need to add? The noise we add is going to be inversely proportional to the privacy parameters. So you see the mu on the bottom. One thing I didn't exactly mention is, so actually the privacy parameter is like mu over square root of capital T. So the reason is that you lose mu over square root capital T in every of capital T iterations. So by composition, then you get mu overall. And then there's the more problematic part. So in order for this Gaussian mechanism to work, you need to have bounded sensitivity of the gradients, right? So here, as it's written, it's going to be proportional. The noise is proportional to capital B, which is some upper bound on the norm of the derivatives. Okay, and this capital B is going to come back and bite us a little bit. So as I mentioned, the iterates themselves, it's solving a convex problem, but you have a nice closed form solution, so there's no problem with computation. All right. So as I said a moment ago, you can easily see that this algorithm is going to be mu Gaussian differentially private, because every step is going to be mu over root T Gaussian differentially private. And therefore, after you do it capital T times, it's certainly private. Now, what can we say about rates of convergence? So I'm not going to dig into the technical details too much. I think I want to highlight the challenges, not the technical challenges, but like the actual challenges with, you know, what is still to be desired with our guarantees. So suffice it to say that in order for this algorithm to work well, your loss function has to be nice enough, right? So if you have the loss function and you don't have the L1 penalty, you need it to be sort of smooth enough. And in high dimensions, you can't really guarantee strong convexity in all directions. So strong convexity is what you would like for fast convergence. But with the canonical example of the lasso, if you look at your lasso, which is a quadratic loss, right, then the point is that the Hessian is a PSD matrix, but it's a low rank matrix when the number of dimensions is larger than the number of observations. So it's only convex, strongly convex in certain directions, and in other directions it's completely flat. So you don't have nice strong convexity. But sort of the magic of all the statistical analysis is that that's good enough, because it turns out that you can prove that when you're optimizing the lasso, you just walk along the convex direction, so you still converge quickly. So the same story, of course, comes out in some slightly more, I don't know, glamorous way, or that's not the right word, but okay, it's a slightly more complicated way when you have to add noise and deal with privacy. But at the core, you know, your loss function had better satisfy certain properties that are similar to what you would need if you were just analyzing lasso. Okay, so we have some notion of smoothness, we have some notion of strong convexity in certain restricted directions. Okay, so then the type of guarantee we have looks like this. So let's just stare at the important parts. So the important parts are that well, first of all, the guarantee we have is just a local guarantee. We have some ideas for what to do about the global analysis, but it's not that elegant. So the local guarantee, local convergence in optimization theory says that if you start close enough, something good happens. And that's as opposed to global convergence, which says that if you start anywhere, then something good happens. I mean, maybe something sort of good happens for a while and then something really good happens after that. But we're just saying, okay, suppose you start sort of, you know, within some constant radius of where you want to be. Then, assuming that your sample size is large enough, you are guaranteed that the final output is going to be close to the global optimum. and the amount of error is like this. So then you might say, well, wait a minute, I thought there was this cost of privacy. So what happened to the usual parametric rate? And the answer is that you use a triangle inequality. So what you're trying to converge to is not the global optimum of your ERM, it's the actual parameter. So you want to converge to theta naught, and if you use a triangle inequality, then you get your sort of usual parametric rate, like square root P over N here, and then the first part would be the cost of privacy. Okay, so it all looks great. You know, a number of iterations is logarithmic. Even the regularization parameters look like you would get for the Lasso. If you're familiar with Lasso theory, the number of samples, it even scales like k times log p. So what could be, I mean, you know, maybe the first term is problematic, but square root of k is smaller than k, so it all looks great. Okay, so the hidden problem, though, is that if you deal with this completely unbounded data domain, then despite our best efforts, we can't make B be dimension free. So B ends up having some dependence on P, something like square root of P. And that just sort of, you know, I mean, we sort of suspect that this might be necessary when you're doing private high dimensional regression, but we can't prove it yet. But it makes us very unhappy because we would really like to say that, you know, the cost of privacy term is going to generally be dominated by the other term, at least for a constant mu, and that's not where we are. Okay.
Sorry, can you clarify what is this capital B?
Yeah, so this capital B is a bound on the gradients of the loss function. So in some slides to come, I'll unpack for you exactly why we can't really, you know, deal with the problem. So, or why we can't kill it completely when we are in an unbounded data domain. So I mean, everything that I've stated is true, right? It's like if you have this bound on your derivatives, which you could do for a Huber loss, for instance, right? Then if you add this much noise, then you have, you know, n is scaling like that. But the problem is that if you have unbounded, if you have these leverage points, then B might scale like square root of B. Okay. So just to break it down, right? I think here is something that's saying, okay, well, if you want to talk about cost of privacy of high dimensional regression, then you would get some sort of rate that looks like this. Okay. So maybe I won't really say too much about fast rate, slow rate. We're not really sure if there's a dichotomy anyway. So R prive is this error that we can get up to. If you go back here, so R prive is the order of the squared L2 error. And R prive is generally going to be something small because you assume that your sample size n is larger than the stuff up on top. So for various reasons, we were sort of bent on proving a stronger error guarantee to say that it's not just R prive, but it's R prive squared, it's something even smaller. The reasons being that if you sort of look at the dependence of the rate on various parameters, in the low dimensional case, we can drive it lower. The game in statistics, in theoretical statistics, is like, you know, oftentimes you can derive whatever rate you want as long as you assume enough stuff. So here in high dimensional statistics, it's like, what do we assume about the relative size of n, of p, of the support size k, and so on. So we worked pretty hard, and we were still kind of working on this part to try to get down to this error. And in order to do that, our results look a little bit worse. So basically, n looks like the square of what it was before. That's maybe the best way to summarize it. And if you go back to the previous slide, right? So, or maybe I should say like it's that plus the second part. So the first part is the part that depends on privacy. And then the second part is this k log p. So here we're saying, well, we now square it. And if b were a constant, we wouldn't really care. Because if b were a constant, we would say this term is now order k, but it's dominated by k log p, so everyone's happy. But now if b depends on p, then we're not happy anymore. Okay, so let's talk about an example so that you can see what I'm talking about more concretely. So let's look at the linear model, sparse linear model where the parameter beta naught is k sparse. Then we look at this bound on the derivative. What does that look like? So as I said, we're going to use a Huber function, right? So we use this Huber loss function, and the Huber loss function has the property that the derivative is bounded by gamma. So you take a derivative, and what comes out is L gamma prime, which is bounded by gamma. But since you're taking a derivative with respect to beta, then xi also pops out. Okay, so we see that, you know, this is why a Huber loss is great for getting rid of for controlling deviations when y is sort of an outlier. But when the x's are really big, then you have a problem. So what we do is, as you saw in an earlier slide, right, we're going to apply some weights. So the idea is if you apply a weight inside the loss function and you multiply it by this residual, then we take a derivative, the weight pops out as well. So if you can control the weight, like if you have a weight W of xi multiplied by xi and that product together is bounded, then this at least it solves some of your problems, maybe not all of them. Okay, so that's what we did. We'd also done something like this in a low dimensional case. And then the other thing that we did, I guess, because we were sort of throwing ideas from robust statistics at the problem. So I think in a lot of the theory of Lasso, for instance, in high dimensional statistics, we often just talk about trying to solve for beta. But then there's this hidden dependence on sigma. So even if you're talking about Lasso theory, the variance of the residuals is relevant in your regularization parameter. It turns out that in robust statistics, this is something people cared about a lot, not just in Lasso, but even in low dimensions, is that, you want something that allows you to learn both beta and sigma so that you're not trying to make any weird choices. So as a result, we decided to do a joint optimization problem over beta and sigma, because why not? So now we can privately estimate beta and sigma. So if we put everything together, we look at this loss function. So the loss function, the things I want to draw your attention to are the fact that we have now introduced a weight. So this weight is downweighting points to try to give us something to hit the xi's when we take a derivative. And then the other weird stuff with sigmas is just so that we end up with a convex function in beta and sigma. Okay, so it's a bit complicated, but it turns out that this is actually jointly convex in beta and sigma. The first time I saw that, I was really surprised, but it's a trick due to Huber from when he was studying linear regression. So the simplest thing you would do, where you just take the residuals and divide them by sigma and apply a Huber loss, that is not jointly convex in beta and sigma, because you have a beta in the numerator and a sigma in the denominator. But there's these things you can do, like multiplying by sigma and adding sigma to make things consistent, and it turns out that this is jointly convex. Okay, great. So then L gamma is your Huber loss. So now let's talk about the weights. So these weights, if you remember, are coming because we want to take a derivative with respect to beta, and we want the weight times x to be bounded, right? So so the standard thing that people do in robust statistics is they basically look at a weight that scales inversely with the L2 norm of x. Because what that does is that ensures that the weight times x is bounded in L2 norm. And in robust statistics, they then talk about optimizing. So what is the constant that should sit up on top? Or if you have data that aren't isotropic, then maybe you have some matrix that's multiplying by the x on the bottom and so on. Okay, but the problem is, if you're talking about high dimensional, if you're being a bit more careful about dimensionality, then it turns out that the weight that you should be multiplying by, you can't just squash down the x's. You actually need to be multiplying by square root of p in order to retain any information in all of this. The best way to think about it is like this: if you just have x's which are IID, which are standard Gaussian in p dimensions, right? The norm is going to go like root p. So if we are always multiplying by 1 over root p, this is bad. Like something terrible is going to happen to our estimator. If that's not convincing enough, so here's another take on it. So in some of the earlier statements, well, there was this hidden, okay, maybe I should go back to that. So in some of the earlier statements, there were these, there's this tau that comes up, and the tau is related to the curvature of the problem. If you're familiar with Lasso theory, it's like the restricted eigenvalue parameter. So that usually shows up as a reciprocal in your rates. That relates to the smallest eigenvalue of your Hessian matrix. Okay, so now we think about what happens in this case where we're squashing down our weights. So if we squash down our x's and we don't multiply by root p, then your Hessian matrix is going to get squashed as well. So the minimum eigenvalue is going to go to 0 really, really fast, inversely with p. And that means that if we plug the results into our theorem, so our theorem is still true, right? But the rates that we get, they're shooting up with a p, which we don't want. Okay, so that's why we can't, just sort of naively squash things away. So if we, but then if we choose these weights now so that they scale with root p, so that our eigenvalue parameters are all fine, then the problem is that the capital B is going to scale like root p. So I personally tried very, very hard to come up with some magical rescaling of like everything in this problem to make B controlled and yet make the eigenvalue, make the curvature of the problem preserved, but I couldn't find a way around it. So, but maybe on the plus side, right? If our x's are bounded, which in fact, is an assumption in most of the previous theory in this area, then this problem goes away. So if the x's are bounded, then we have no need to introduce a weight, so everything is great. In fact, we can deal with unboundedness in our y space, and everything is great, just with a Huber loss. Okay, but because we sort of tried to cook it all in, we're getting this dependence on B that we don't particularly like. Okay, so yeah, so then there's some sort of technical stuff that I don't really want to go into, right? So I mean, even with those choices of weights, I sort of said, in principle, right, if you choose this kind of weight, then your curvature won't get squashed as P grows, but you have to actually prove this. And in order to prove that, we needed some assumptions on our X distribution and our Y distribution to make this hold. And we ended up using some kind of isotropic log concave assumptions. But to give you sort of revealing the worst of our dreams, which is, we have this rate, we have the root k log p over n, which is the parametric rate, and then we have a k root p, which, unless your privacy parameter mu is growing fast enough to kill the root p, like this is the term that's now going to be dominant. And if you look at it in terms of sample complexity, you see the same behavior. We would like to say that the sample complexity only needs to scale linearly with the sparsity k, but now we're saying that in the presence of privacy, we need it to also grow polynomially in P. Okay, so maybe very quickly, I will go through the second example. So the second example is just kind of, it's a demonstration of the fact that our theory can hold more broadly than just linear regression. I mean, really what we had in mind was linear regression. But we'll look now at a mean estimation problem. So this is a multivariate mean estimation problem. You observe vectors xi, which are beta naught plus epsilon I, where epsilon I is coming from some multivariate parameter. I should say that that this is a problem that has also been studied separately in differential privacy. And I mean, there are certain limitations of our approach. And so for instance, like in our work, we assume that epsilon I comes from an isotropic family, but in other work in differential privacy, epsilon I might have a covariance matrix that's not the identity. Then you might want to measure accuracy of your estimators in terms of Mahalanobis distance. So we don't do anything that fancy. And then we needed some assumptions in epsilon I to make this all work and have good concentration. I won't go into the details here. Basically, we wanted to avoid assuming that epsilon I was sub-Gaussian because we thought that wasn't interesting enough. So we sort of, delved into like what assumptions do we need for our concentration to work. Okay, so the idea was we want to use some sort of a loss function that has this bounded derivative loss property. And then we decided to take a page out of robust statistics, right? Because things that work in robust statistics tend to have some analog that works in privacy. And quite recently, Timothy Mathieu, who works in high-dimensional robust statistics, came up with a method for robust multivariate mean estimation. He wasn't interested in privacy, but he was interested in doing empirical risk minimization with a loss that's suitable for robust multivariate mean estimation. And the idea is, okay, well, generally in robust statistics, having a bounded derivative on your loss is good. And if that's the case, which it is here, then we can use it in our work too. Just as a side note, what's hard about multivariate? Well, what's hard is that you would naturally like to apply your loss function to the difference xi minus beta naught, because that's the analog of what you would do in linear regression. So you would want to apply the Huber loss, let's say, to xi minus beta naught, or xi minus beta. But the problem is that the Huber loss is a univariate function. So you could think about some like multivariate Huber loss, but that gets kind of ugly and complicated. So I mean, Mathieu's idea was to apply it to the norm of xi minus beta. And then he showed that this has some nice properties. So we did the same thing here. And then, but it turns out that to the best of our analysis, we again had the problem that, if we want to rescale things appropriately, then the best we could do to make the curvature still constant order instead of something shooting down to zero was to make this upper bound b square root of p. So again, I personally tried very hard to avoid this, but could not. Okay, and then maybe one last thing is, I think in this analysis of mean estimation, another thing that kind of came out, which was nice, was that so we have to be a bit careful about non-differentiability in this case, because if we look at our loss function, it looks like this. And in, the Huber loss is first order differentiable, but not second order. So that was not a problem in our earlier analysis for linear regression. But when we're analyzing this objective function, then the non-differentiability of the norm at 0 says that this loss function is actually not differentiable everywhere. And we can't exactly say that, with high probability, it's not differentiable at, certain points because of randomness, because the problem is, we generate our random data and then we run an optimization algorithm on top of it. So it's kind of hard to control, where exactly we're hitting. So we had to be a bit more careful, and we showed that at least in this case of this objective function, the theory still goes through. We can analyze our iterates and say that we have fast convergence to a point that we want. So this is what the rate looks like. It's basically the same slide that I had for linear regression, because at this level of description, it's same sort of orders of the errors and the sample size. Okay, I think I will skip this part. I mean, if the proof is kind of like, look at the proofs that you would normally use without noise, add some noise and see what happens, right? And in the low dimensional case, that more or less worked. In the high dimensional case, the problem was that, well, that's what gave us the slow rates. And in order to get the fast rates, we had to work a little bit harder. So in the slow rates, we basically said, well, you're adding noise, and generally you have inner products of this noise, Gaussian noise vector with other stuff. So if you do the coarsest possible thing, use Holder's inequality everywhere, then if you just bound the infinity norm of your Gaussian vector globally, then you can sort of proceed and analyze how that noise is propagating. This gives you the slow rates. But if you want to be a bit more careful, then you need to use the fact that when you're hitting this Gaussian noise with a vector, actually the vectors that you're multiplying them by are like the iterates that you're getting through gradient descent. And now if you're doing high dimensional gradient descent, it turns out that your iterates are getting sparser and sparser. So even though they're dimension p, and all these p coordinates might be hitting your error vector, right? As you get closer and closer to the solution, your iterates are getting more and more k sparse. So you can prove that after a while, they are actually order k. So then the amount of noise that you're getting is sort of order k rather than order p. So that's how we get the fast rates. But in order to derive this, we need some extra assumptions along the way. Okay. So I'll wrap up. So in low dimensions, I think we have a nice theory, but looking back, it was much easier than what we're analyzing here. We analyzed some version of noisy gradient descent, some version of noisy Newton's method, and came up with rates of estimation for various regression and different statistical estimation problems. In high dimensions, I think we were the first to analyze a version of noisy composite gradient descent. And in particular, right, we're working in this setting where the xi's are in an unbounded domain, so you can't just you can't just sort of use a Huber loss or truncate everything. You need to, well, in our case, like from our analysis, we sort of suspect that maybe that's what's causing that there's some fundamental bottleneck, that your sample complexity needs to be larger, needs to scale polynomially with p, and your error has to as well. What I didn't go into, but we also spent a lot of time trying to prove, is confidence intervals. So in high dimensions, so there's this whole several lines of work now on what's called debiased Lasso. The idea is the lasso itself, it has nice estimation error properties, but if you look at the asymptotic distribution, it doesn't have nice asymptotic normality. So people do a debiased version and analyze that estimated version to create confidence intervals. So we tried doing the analog in high dimensions. And again, we ran into some bottlenecks because, so maybe the best way to summarize it is the debiased lasso involves an estimate of the inverse covariance of the x's, because that's involved in your step. And if you start taking inverse covariances, these are now p by p matrices. And you need to make it noisy, because this is something that depends on your data, your xi's. So if you're trying to make a p by p matrix noisy, then you're adding some p squared dimensionality Gaussian. And in order to make sure that that noise that you're adding is smaller than the original signal, you need much stronger assumptions on your relative scaling of n and p. Okay, and so future work is, well, we're still trying to wrap up the high dimensional paper, but global convergence theory. So as I said, we have some things to say about what to do when you initialize further away, but it's not really that elegant. Lower bounds. So I've kind of claimed that we think that that the polynomial dependence on p is necessary. I guess we sort of feel at this point like this should have worked if it was going to, but that's not a good enough proof. So, you know, we want to look more into lower bound techniques for unbounded data domains. And then it would be nice if there was some second order version of composite gradient descent, but it's, you know, first of all, we again have to be adding noise to P by P Hessians. And secondly, Newton's method in high dimensions is sort of, you know, much harder computationally. So we're not sure what the right story is here. So thanks a lot for your attention. I'm happy to take questions.
Good. Yeah, thanks a lot for the presentation. I think if anyone wants to ask questions, you can feel free to unmute. Maybe I can start with one question. So you mentioned this Hoover loss, and it seems that it has this parameter gamma. Is that right?
Yeah.
That determines the range where you
Right.
just kind of forget about the about the values. My question is, what do you do to choose this parameter of gamma? Do you do anything in particular?
Yeah, so that's sort of the magic that came into the really complicated objective function I pulled up. So the point is that when you jointly optimize over beta and sigma, then you can forget about gamma. So another way to put it is if you didn't have dividing by sigma, then your gamma should be calibrated to the noise, right? It's sort of calibrated to the noise standard deviation. But if you now jointly optimize over beta and sigma, so you're dividing by sigma, then gamma could be whatever you want. I mean, I would just choose one, but I guess in classical robust statistics, it's 1.345. So that's what we say in our paper.
Good. And maybe the other question I had, I found this quite interesting to use these weights to remove the effect of the inputs. And I was trying to think about, I mean, I'm not an expert in this area, but I found these weights to be kind of thinking, for example, as if you had like a squared loss, these weights would look like a bit like the noise in your model, or if you have like a, with a squared loss, you typically assume Gaussian noise. And then if you have like a weight there, it would be something similar to kind of the inverse balance in your Gaussian noise. I don't know if there is any interpretation that you can make on these weights. Probably not so much.
I'm not sure. I mean, but that would be like that would be a function of the residuals rather than the x's themselves, right? Maybe.
Yeah, I was thinking that, for example, you could interpret that you assume that maybe the noise in your imagine that you could imagine that there is some noise in the data in the targets y, and this noise increases maybe as a function of the inputs. For example, then what is going to happen is that if you assume that there is very high level of noise when the input is x, maybe has some large magnitude, then you would ignore that data point, because you would say, oh, this data point is not very relevant. I mean, I don't know, it seems to be like some some similarities there between maybe heteroscedastic. You have this heteroscedastic
maybe
where the data, the noise can be input dependent, but obviously this is not it's more, it's kind of the same underlying idea, no? That when you have like large inputs, you don't want them to be affecting your estimators. And
yeah, that's true. Yeah, I mean, I haven't personally worked much on heteroscedastic noise, but you're right, that would be one model for it, right? It's like because it's heteroscedastic, you need to wait by the exit. Yeah.
Good. I don't know if anyone has any other questions. No. Good. So yeah, thanks a lot for joining us, and yeah, looking forward to seeing you around in the activities of Ellis. We are organizing a summer school. There is a summer school going on in the summer, and the details are in the website in case, I don't know, anyone, if you are interested, or anyone, maybe your students or anyone is interested as well.
Okay, great. All right, well, thank you.
Thanks a lot. Bye. Bye.
Okay, yeah, take care. Thank you.